me record the class. Anyone has any questions? Okay, so we have talked about 3 tests, right? So today we're going to learn another test. Hello. Yeah, before I start talking about this comparison test, anyone has any questions?
Yeah. Is homework due before class or like until the end of the day, before 12
Oh,
o'clock?
what did I put? Let me see. Let me go back to see, because sometimes I forgot to change the date time. Oh, it's 10. It says here it's due Thursday, March 31st, 22nd, 10 a.m. Do you have enough time to do it?
Oh yeah, I think like I always thought like it was due before 12. That's why.
Oh, okay. Wait, sometimes I try to change it to later time. Sometimes I just forget about it. I forgot to do that. Let me open the test again. Okay. Oh, I have. So this sharing is a little bit tricky. All right, let's see. Anyone has any questions? So homeworks are due at the end of the day. Fujun, you have to see the time. Let me show you. So this is tricky part. Let me change the screen, sharing screen. So let's go to my open math. Let's go to this page, right? So you see homework is due, right? It's due on the calendar. It only tells you day, don't tell you time. So what you have to do is you have to go to the homework. You see homework 12 is March 31st at 10 a.m. Homework 11, 10 a.m. But sometimes I remember to change to afternoon. So you see homework 10 is 10 p.m. Homework 9 is 10 p.m. I will try to change it to 10 p.m. because the system, by default, the system set to 10 a.m. Sometimes I just forget to change it. But I will try. I will remind myself to change it to 10 p.m. But for you, to be safe, just try to finish before 10 a.m. if you could. All right, now let me change my sharing screen. All right, so we're at chapter 5. So we have talked about divergence test, integral test, right? And we talk about couple of important series, like harmonic series. We know it's a very famous series, not convergent. And we learned geometric series. Geometric series, if the ratio, absolute value of the ratio less than 1, we get a very nice formula to find which number it converges to, which is the initial term divided by 1 minus the ratio. And then we have learned the divergence test, right? Divergence test will be able to tell us the series divergent, but we won't be able to use it to prove the series convergent. So we can only prove a series is divergent. And then we talk about integral test. So if the an term can be expressed as a function, so we can use the integral, can come from the finite world, a summation of infinite many terms, to think about the integral of the function. If the integral of the function converges, right, that means the series converges. If the integral diverges, that means the series diverges. So today we're going to talk about comparison test. So I guess I have to reshare my screen. Comparison test. So we want to use comparison test to test a series for its convergency, right? And we use a limit convergence test to determine, what number it converges to, the series converges to. So let's see these two series. So the first series is, summation of infinite many terms of 1 over n squared plus 1, or n is just a natural number. And this series looks very similar to the convergence series, 1 over n squared, P series, right? Right, I forgot to talk about P series. So geometric series and P series, harmonic series, 3 very famous series we have to remember. So P series says, so it's 1 over n raised by P, right? So P here is 2. So if P is greater than 1, so that series converges, okay? And even we will have a very nice formula for it to tell 1 over n squared. 1 over n squared, 1 over n cubed, we can come up with a formula to calculate its, the number it converges to. But if P is less than or equal to 1, the series diverges, right? So that's a P series. So we want to compare the 1 over n squared plus 1 to 1 over n squared series. So since the terms in each of the series are positive, the sequence of partial sum for each series is a monotone increasing. So that means 1 over n squared plus 1 is greater than 0, but less than 1 over n squared. So for all positive integers n, right, or for all natural numbers of n, the kth partial sum of sk can be represented as this. We'll sum up 1 to k terms, 1 over n squared plus 1. N goes from 1 to k. And the sum, of course, is less than the summation of k terms of 1 over n squared, right? And of course, the finite k terms will be less than infinite many terms of 1 over n squared. So since the series on the right, so we know P series, right? N squared is a P series, because P is just equal to 2. 2 is greater than 1, and we know 1 over n squared. This series converges, right? So if this series converges, the series less than it must converge also, right? So series of sk converges. And then we can conclude, so sk is monotone increasing sequence. So by monotone convergence theorem, sk converges, right? Because if it's not monotone, we won't be able to tell. But because it's a monotone increasing sequence, so sk converges. And then we can conclude, right, the series on the left-hand side, 1 over n squared plus 1 converges. So similarly, consider the series 1 over n minus 1/2, right? So that series looks similar to divergence series 1 over n, and is smaller than 1 over n, right? Because the denominator is smaller. And the 1 over n series we know is harmonic series. Famous harmonic series diverges. And of course, the series is always bigger than it. It has to diverge, right? So this is by monotone convergence or monotone divergence theorem. Actually, it's called the monotone convergence theorem. So that's how we compare, right? So we compare a convergence theorem we compare a series, you know, we want to prove a series is smaller than a convergent series, right? If the bigger one converges, the smaller one must converge. The other part is, if we know the series is close to a divergent series, and it's even smaller, it's less than a divergent sum, divergent series sum of the divergent series, then we can conclude, you know, if the smaller one diverge, you know, if the smaller one diverge, the bigger one must diverge, right? So when we compare the convergence, we want to compare the bigger one converges, the smaller one converge. So, you know, versus divergent. So this is a comparison test. So basically we find a series, a famous series we know about to compare with. Okay, any questions? So here we have this, the first one is a P series, where we compare to a P series. And the second one is we compare to a divergent harmonic series. Well, this just gives us a couple of values to show, right? So sum of one term, smaller, sum of two terms, smaller, sum of three terms, smaller, you know, so on and so forth. It's a little bit bigger than the divergent, right? Two terms bigger, three terms bigger, four terms bigger, so on and so forth. So every summation is bigger than the harmonic divergent series. Okay, let's see the theorem itself. Comparison test. So we have two parts. The first part says, suppose there exists an integer n. Okay, so this capital letter N, it just allows us to forget about the finite sums. So basically, you know, we don't require a series totally fits into the comparison test, comparison situation. So it means allows us to ignore the first finite terms. So for n, for little n greater than or equal to the capital letter N, so if we have an less than or equal to bn, but all positive, all non-negative terms, so then we can conclude if bn series converges, then we can conclude an converges, right? Because its sum is always smaller than the sum of bn's. The bigger one converge, the smaller one must converge. So the second part is the opposite, right? Also, this capital letter N allows us to forget about the finite many terms. Then, if Bn diverges, right? If Bn now is less than An, so An, the one we're trying to find, An, is always bigger than An, bigger than Bn. And if we can show Bn, the smallest one, the smaller one diverges, then we can conclude the bigger one diverges also. Right? So this is intuitive, right? So the first part and the second part. Right? You know, if we want to prove convergence of a series, we find a bigger one. If the bigger one converges, the smaller one must converge. If we want to prove a series diverges, right, we have to find a smaller one diverge. If the smaller one diverges, the bigger one must diverge also. So this is a comparison test. Anyone has any questions? Okay. Okay, I think I recorded. Can you use this test for all series? Not really. Think about it. This is convenient for P series. If this one works for everything, you know, we won't be needing all other tests. So we have so many different kinds of tests. It's just for all different kinds, covers all kinds of situations. But it definitely works for a lot of series. Okay, any other questions? Yeah, it's very good for P series. You're right. It's very good because it's obvious, right? For P series, it's very good for P series and for one harmonic series. Yeah, right. But that's a good question. You can, when you do homework, right? You can put the homework of using integral test, using divergence test, right? And now we have a comparison test. When you do one homework, you can think about the other. Oh, may I apply this test for other, homework for other kinds? So now let's see these examples. All right, so we have ABC3 series. Okay, see the first one is 1 over n cubed plus 3n plus 1. And you probably have an idea, right? What do we want to compare with? We want to compare with P series, 1 over n cubed. So this kind is obvious. Or B, we have 1 over 2 raised by n plus 1. And you want to compare with geometric series, right? Because you see 1 over 2 raised by n. And C, 1 over ln n. Right, which one we can find to compare with? Let's see the solution. So 1 over n cubed is a P series and a convergent P series because P equals 3 is greater than 1. And 1 over n cubed plus 3n plus 1, the denominator is much bigger because the n is non-negative. So the denominator is bigger, so the whole thing is smaller. So 1 over n cubed plus 3n plus 1 will be always less than 1 over n cubed for every positive integer n. So because 1 over n3 series convergence is a P series, right? Because P is greater than 1, it converges. So we can conclude this one converges. And B, we want to compare the series in B to half raised by n, geometric series. And because the ratio in this geometric series is half, which is less than 1, and we know it converges, right? It converges. Then 1 over 2 raised by n plus 1, the denominator is always bigger, so 1 over, a bigger denominator is always smaller. So it's smaller than the convergent series, so we can conclude this one must converge also, because it's bigger than the convergent one. So we can compare with P series, we can compare with geometric series. So let's say C. C, we want to compare with 1 over n, harmonic series, right? So 1 over ln of n is always bigger than 1 over n. Why? Because ln of n is always smaller than n, right? Think about ln1. ln1 is 0, right? 0 less than 1. You can keep going. lne equals to 1. 1 is smaller than e itself, so on and so forth. So 1 over ln n is always, the 1 over ln n is always greater than 1 over n. Because 1 over n is a harmonic series, divergent, So we can conclude 1 over ln n diverges. Okay, any questions? We have 3 types, right? So the first two, convergent. We want to prove convergent. So we compare with the P series, we compare with the geometric series. And the C, when we want to prove diverges. To prove diverges, we can compare with here, we can compare with harmonic series. It's bigger than harmonic series, so it diverges because harmonic series is divergent. A big one must diverge also. Anyone has any questions? Okay, keep going. Okay, checkpoint. Everyone try 5.16. Let me take attendance. Okay, Raw has diverges. Golem says converges. Converges. Okay, Damon says compare it to n over n cube. Converges, converges. Okay. N over n cube or 1 over n squared. That's what you mean, right? Yes, definitely. Yes, we want to compare. Yeah, we can compare with n over n cube or 1 over n squared, right? 1 over n squared, we know is P series converges, and this one is always smaller, so it must converge also. Yes. So the little tricky part is the numerator has n, right? So we can only consider, we just consider, so when n goes to infinity, we only consider the leading terms. The leading terms in the numerator is n, leading terms in the denominator is n cubed. Because when n approaches infinity, the lower terms can be ignored. The lower terms can be ignored, n plus 1 can be ignored. We only consider n over n cubed. Yes, it does converge. Anyone has any questions? Okay, Paul, your guessing was diverges. Right? Do you see why it's not divergent? It's convergent. We compare with n over n cubed or 1 over n squared. 1 over n squared is a P series. Oh no, the opposite. Opposite, Raw. P greater than 1, the series converges. P less than or equal to 1, the series diverges. Okay, greater than 1 converges. That's okay. That's okay. Yeah. So we're here to learn. All right. Okay. Geometric sequence has this form, has 1 over n, 1 over, let's see, 1 over number, 1 over a raised by n, right? 1 raised by a number. So this a, let's see, 2, could be 2. Let me just put it there. We see geometric sequence It's this. It's 1 over a number raised by, it's exponential function. Remember that? The exponent, the variable appears in the exponent. So geometric series, we can think as an exponential function. But P series is not, right? P series, the variable is in the base. It's 1 over n raised by number. Let's think about 1 over n squared. You see the different places of variable? Okay. All right. All right. All right, so that's comparison test. Comparison test requires us to remember geometric series, remember P series, right? And also remember monotone convergence theorem. Or sometimes maybe we have to use integral test. And a comparison test requires all the terms, all the n's be non-negative. Okay, be non-negative. Okay, going further, something more, it's called limit comparison test. So the comparison test works nicely if we can find a comparable series. So that means we have to remember, you know, a couple of good geometric series, a couple of good P series. So to find a comparable series, satisfying the hypothesis of the test, right? Either we find a convergent series or we find a divergent series, then we compare with. However, sometimes finding an appropriate series can be difficult, right? Let's see this series, 1 over n squared minus 1. So this is always bigger than 1 over n squared because the denominator is smaller, right? So if it's a big one, if the series is bigger than the convergent series, we won't be able to make any conclusion, right? Because the smaller one convergent. If the smaller one convergent, you know, we won't be able to see a big one. So maybe the big one doesn't converge, right? We can only prove if the big one convergent, a smaller one converges too. But if the smaller one converge, we won't be able to conclude the big one converges. So we won't be able to compare 1 over n squared minus 1 to 1 over n squared, because 1 over n squared minus 1 is always bigger than 1 over n squared. So we won't be able to use comparison test. So what do? We want to use limit comparison test. So limit comparison test requires us to do this. So we use the an term divided by bn term, then we take a limit of it, right? We want to see the ratio. Where does this ratio, if this ratio converges? So we take an, then we divide by bn. All right. So this is called a limit comparison test because we have to take a limit. We compare those two by taking ratio of those two. We take a ratio of those two, then we take a limit of this ratio. So that's why it's called a limit comparison test. Okay, let's see this example. So if limit of the ratio an divided by bn equals a number not 0, then for n sufficiently large, so an is about L times bn, right? Because L is the limit. So either both series converges or both diverges, right? So if we can prove this, this means, you know, these two series, one is just a scalar of the other, right? So one series is just a scalar of the other series. So that means they're closely related. If we can prove one converges, the other one converges. If one diverges, the other one diverges, right? Because they're differed by a scalar. So for the series of 1 over n squared minus 1 and 1 over n squared, we can compare a n term and b n term, the nth term. So we would do 1 over n squared minus 1 divided by 1 over n squared. Then we'll take a limit of it. Let n goes to infinity. So what do we have? Well, we'll take a limit when n approaches infinity. We only consider the leading term, something called the ignore rule. So the leading term in the numerator is n squared, leading term in the denominator is also n squared. We say the limit goes to 1. So this a n b n, the limit of a n b n when n approaches infinity, it goes to 1. So since 1 over n squared converges, we conclude that 1 over n squared minus 1 also converges. Right, also converges. So those two is comparable. When the limit of the ratio of the two sequence nth term equals to a number, yeah, does not equal to 0, equals to a finite number but not 0. The other case is the limit comparison test can be used in two other cases. Suppose the limit equals 0. The limit of the ratio of an and bn equals 0. In this case, an divided by bn is a bounded sequence. As a result, there exists a constant m, right? Such number exists a number such that an is always less than or equal to the number multiplied by bn. Of course, right? Right? If L is 1, M could be 2. If L is 2, M could be 3, so on and so forth, right? Whenever we're dealing with a finite number, we can always produce one bigger than it, or we can always produce one smaller than it. So therefore, if Bn series converges, then An converges. Because if Bn converges, it converges to a number. It converges to a number multiplied by any finite number is still a finite number, right? If that converges, the smaller one must converge also, right? So if the limit equals 0, right, so we can make this conclusion. The third case is if the limit does not exist, right? If an, the ratio of an and bn, take a limit when n runs to infinity, it goes to infinity, which means the limit does not exist, which means the ratio of the two terms is not bound. So it's an unbounded sequence. If it's unbounded sequence, for every constant term m, there exists an integer n such that an is greater than or equal to mbn. For all n greater than or equal to n. Again, this capital letter N just allows us to ignore finite terms. Therefore, if a series of Bn diverges, then the series of An diverges as well. All right. So this is a limit comparison test. So we're comparing, there's no way we can compare using comparison tests. So what do? We do one step further. We'll take a limit of the two terms, nth term of each. Then we say if it goes to a finite number, so that means they converge. So that means that one is a scalar of the other. Right? So they're closely related. So An equals a number multiplied by Bn. If An converge, Bn converges. If An diverge, Bn diverges. Vice versa. If Bn converge, An converges. If Bn diverge, An diverges. Right? Because they have An and Bn have such tight relationship. Right? So one is a multiple of the other. If one converges, one is finite. You multiply finite number with a finite number, it's still finite. So back to the example, we take a limit, we get 1. Right. So since 1 over n squared is p-series converges, so we can conclude 1 over n squared minus 1 also converges, because this is an equals 1 times bn case, right? The second case, the first case. So an equals to 1 times bn. So one converge, the other one converge. One diverge, the other one diverge. So that's this example. Anyone has any questions? All right, let's see the exercise. Okay, let's go over the theorem. So limit comparison test, we have 3 bullet points. So a and bn, all the terms in the series non-negative. So if the ratio of the limit equals to certain number, certain finite number, which is not 0, then what happens to one? It will happen to the other. If one converges, the other one converges. If one diverges, the other one diverges. The second one, if the limit of those to reach the ratio equals 0, if bn converge, then an converge. So notice this, we won't be able to tell convergence, right? This only say if bn converges, then an converges. If the ratio equals to 0, if the limit of the ratio equals to 0. So we won't get the second part about divergency. Okay, we can see nothing about divergency. Okay, the third point is, if the limit of the ratio does not exist, then if bn diverges, then an diverges. All right. So bn is like a series we really know, we want to compare with. An is a series we want to find out is convergency or divergency. Right, so these 3 situations for limit comparison test. So if the ratio is a number, then both are, what happens to one, what happens to the other. One converges, the other one converges. One diverges, the other one diverges. If the ratio of the limit equals 0, that means if bn converges, then an converges. If the denominator converges, then the numerator converges. What this situation is, if the limit does not exist, right, then we can conclude if bn series diverges, then an series diverges. Anyone has any questions? Okay, maybe with some, let's see, we have some exercise. Okay, let's all try this one. So we have A, B, C, 3 things. All right. Actually, just go through. Let's go through this. This is supposed to be example. Let's go through this. Right? Because let's see the first one. A, what do we want to compare with? We probably want to compare with one P series, right? One divergent P series. If a divergent series, if a bigger divergent series, if a series is bigger and a divergent, we can conclude, the series is smaller than it, it diverges. B, we see that's geometric series, right? Almost, we can compare to a geometric series. And, oh, we won't be able to, because the numerator is 2n plus 1. The numerator is bigger. So what do we want to do is we want to use the limit comparison test. Right? We want to use an divided by bn. Then we take the limit of the ratio and go from there. For 3 situations, we can separate it into 3 cases. C, we have ln of n divided by n squared. Right? So this one, we will see, so ln n of divided by n squared. Is it bigger than harmonic? I think it's bigger than harmonic. Probably want to compare with harmonic series. Can it diverge? Okay, Rajev is asking a question. Can an diverge if bn also diverge when the limit of the ratio is equal to 0? Oh no, that's by third part, right? You see, when it equals 0, that's talking about the convergence. Let me just pull this up a little bit. Okay, you see the theorem is this. When it's equals 0, that's about convergence. Right? So if bn convergent, then an convergent. We won't be able to tell anything about the divergence. So equals to 0. Equals to 0 means, right, equals to 0. That means the denominator grows much, much faster than the numerator when n approaches infinity. So if a bigger one convergent, then the smaller one convergent. All right, it converges anyway if you get 0, right? Yes, if we get 0, and also the denominator one converges, then we conclude the numerator one converges. The third one, you see, the third one is for divergence, right? The third one is if the ratio goes to infinity, which means the limit of the ratio does not exist. So the two, you know, the numerator one is much, much bigger or grows much, much faster than the denominator when n approaches infinity. Right? You can think of an as an exponential function and the bn as a linear function. Exponential function grows much, much faster than linear function. Right? So that means then the limit goes to infinity, or the limit does not exist. Because the numerator grows so fast. The numerator reaches infinity much, much faster than the denominator. The second case is the opposite. The second case is saying, think about the numerator an is a linear term, and the bn is an exponential term, right? So the denominator grows much, much faster, changes much, much faster than the numerator. So that's the 2 cases. But for the second case, we won't be able to tell divergence. For the third case, we won't be able to tell convergence. So this is something about a theorem, corollary, or anything. Okay, Rajab, does that answer your question? Okay. All right. So, right. So, some mathematical analysis involved. Any other questions? So 3 situations, 3 cases. How they got to third step? Okay, let's go back a little bit. You mean, for example, 1? For this one? For example, 8. Oh, okay. For example, 8. So that this one, which is what? Are you talking about, no, you're not talking about this one, right? You're talking about the limit comparison test one. I think I did too much. This one, A. Where is A? This one? Yes, okay. This one, you see P series, right? This one we want to compare with P series. So remember square root of n. What's square root of n? It's n raised by half, right? N raised by half. N raised by half, that means P equals to half. If P equals to half, so P less than 1, so it's divergent, right? The series is divergent. So we want to compare A with 1 over square root of n to P series. Because this series is always smaller than 1 over square root of n, because the denominator is bigger. So then 1 over square root of n divergent, right? It's a smaller one divergent. So the bigger one, must divergent also. That's for A. Well, we can go to the solution. Oh, okay. This one use limit comparison test. Right, because we're talking about limit comparison test. So we can use comparison test or limit comparison test. Limit comparison test, we just have to take the ratio of those two. So an is 1 over square root of n plus 1. Bn is 1 over square root of n. So then when we take a limit, so we get square root of n divided by square root of n plus 1. So we take a limit of that, we get equals to 1. Second situation, right? Remember, second situation says if the denominator series, oh, hold on. So, oh, I don't like this one. Oh, this is the first one. Yeah, this is the first situation. The second situation equals 0. This is the first situation. The first situation says, we take the limit of the ratio. If the limit of the ratio equals to a number, a finite number, that means those two, one is just a scalar of the second. So that means those two series are closely related because they're just scaling, they're just scaled by a number. So if one converges, the other one converges. If one diverges, the other one diverges. All right. And because this one, the denominator one diverges, so we can conclude the numerator diverges. You don't really have to use a limit comparison test. You could also use a comparison test for this one. But how did they get to 1 over 1 plus 1 over square root of n? Oh, let me see what I'm talking about. Oh, this one? You divide the numerator and the denominator all by square root of n. Square root of n divided by square root of n equals 1. The denominator square root of n divides itself equals 1 plus 1 divided by square root of n. So you're dividing square root of n over square root of n. Oh, okay. All right. So if you go back to think the first class you are taking for calculus, something called ignore rule. I don't know if your professor tell you the name. Ignore. So this basically, but rule of thumb is saying just ignore the lower terms, right? So just ignore the lower terms. Just consider the leading terms in the numerator and the leading terms in the denominator, which is square root of n divided by square root of n. Just ignore plus 1 in the denominator. If we have more lower terms, just ignore the lower terms, because when n approaches infinity, all the lower terms, it doesn't matter. Yeah, because the leading term, the consideration is under the leading term. It's the same to say, you know, just divide every term there by the leading term. So, right, when I teach calculus 1, I like to tell my students, just call it ignore. Because when n goes to infinity, all the lower terms doesn't matter anymore, doesn't contribute much. So we only focus on the leading terms. Any other questions? Okay, let's B. B, obviously, geometric series, right? And the ratio is 2/3, it's less than 1, it converges. And we want to compare, so the one we have is 2 raised by 3 raised by n, no, 2 raised by n plus 1, yeah. So 2 raised by n plus 1 over 3 raised by n. But this one is bigger than, this series is always bigger than 2 raised by n divided by 3 raised by n. So we won't be able to use a comparison test, right? So from here, you see, from the second one, the first one, you can use both. You can use a comparison test. You can use a limit comparison test. But the second one, B, we won't be able to use a comparison test, right? Because this series is bigger than the convergence series. Because 2 raised by n divided by 3 raised by n is convergent, is a geometric series with ratio 2/3, which is less than 1, convergent. But this one is bigger than the convergent one. The convergent one is smaller than this, so we won't be able to make any conclusion. So in this case, B, we have to use a limit comparison test. Okay, so when we use a limit comparison test, so what do we get in the end? 3 raised by n, 3 raised by n becomes 1, so we have 2 raised by n plus 1 divided by 2 raised by n. Again, we can simplify this. 2 raised by n divided by 2 raised by n, we get 1, then plus half raised by n. So limit of 1 constant equals 1. Limit of half raised by n goes to 0, right? Limit of half of, because 1 raised by n just 1. So 2 raised by n, the denominator gets bigger and bigger, you know, it goes exponentially, it grows exponentially quick. So it goes to 0 very fast. So limit of the second term equals 0, so that equals 1. So when limit of the ratio equals 1, you know, one converges, the other one converges. One diverges, the other one diverges. But because we know 2 raised by n divided by 3 raised by n is a geometric series with a ratio less than 1, so we know it converges. And then we can even get a number which it converges to. So we can conclude that the other one converges. All right. So example B is a good example. It's a good example because this example, you have to use a limit comparison test. So comparison test will now work. Comparison test compares a convergent series with a smaller one, right? If the bigger one converges, the smaller one converges. But this one is not. This one is bigger than the convergent series. Right? So it's not much bigger, but it's bigger. As long as it's bigger than the convergent one, we won't be able to make a conclusion. So B forces us to use a limit comparison test. So B is not a good example. Anyone has any questions? Okay, let's see C. C, we know ln n always less than n. But you can convince yourself by putting some numbers. Ln 0, well, let's start with ln half. Ln half is negative. Ln 2, which is a negative number. So of course it's less than half. A negative number is less than half. If n is 1, ln 1 is 0. Of course, 0 is less than 1. You can substitute n equals e, all the number, 2.71, a keeps going like a pi. So ln e equals 1, and 1, of course, is less than 2.71a, right? So you can give yourself a couple examples to convince yourself. So ln of n is always less than n. So we want to compare this one with a harmonic series, right? So we take a limit of those two, ln n divided by n squared, then divided by 1 over n. We do the calculation, in the end we'll get the limit of ln n divided by n, right? So ln n, when n approaches infinity, ln n approaches infinity, n approaches infinity. So we get infinity over infinity, which is indeterminate form. So whenever we have an indeterminate form, we can use L'Hopital's rule, right? L'Hopital's rule, we take a derivative with the upper one, the numerator, then we take a derivative of the bottom one. So what's the meaning behind it? So why we're taking derivatives? Because derivative is testing how fast each one is changing, right? So if we won't be able to tell if ln grows faster or n grows faster, one is linear, one is log. So if we cannot determine which one grows faster, we can just take a derivative, because derivative is a speed, right? It's a velocity. It's the velocity of the function. So use L'Hopital's rule. So we take a derivative, we get a 1 over n, then divide by 1. So that just becomes 1 over n. Then we take a limit, and of course, that goes to 0. Right? So that's the reason behind why we want to use L'Hopital's rule. L'Hopital's rule is just a number, right? Just a name. L'Hopital's rule is just a fancy name. But the idea behind it is to compare the velocity of two functions to see which one grows faster as the variable approaches to infinity. And of course, the one grows faster will succeed the one grows slower, right? So in this case, it's a 0, limit equals 0, which means the denominator grows much faster than the numerator. So the limit of the ratio of those two equals 0. Well, that's the second part of the limit comparison test, right? The limit comparison test, the first part is saying, okay, if the limit of the ratio equals to the number, that means the two series is just scaling each other. So if one converges, the other one converges. If the one diverges, the other one diverges. The second part of limit comparison test is saying, if the limit of the ratio equals 0, if the series in the denominator diverges, then the series in the numerator diverges also. Bingo. The series in the denominator is a harmonic series, and which we know diverges. So we can conclude the series of the numerator diverges also. Right? The second part of limit comparison test. Any questions? That was rough. That was rough. That's yeah. That's L'Hopital's rule. Okay. L'Hopital's rule. Basically, mathematical analysis. All right, it's mathematical analysis. Sometimes we give it fancy names. Should I repeat? Okay. Okay, let me try. So let's go back to C. Only see the question itself. Okay, so we want to compare. So we have the series ln of n over n squared, right? ln of n over n squared. So we were thinking, okay, how do I How do I know if this series converges or diverges? Or I'm thinking, you know what? I can compare this one with n over n squared, right? Because ln of n is always smaller than n, right? Again, think about ln half, right? It's a negative number, which is less than half. Ln 1 is 0, which is less than 1, right? So that is to say the logarithm function is slower than linear function. Does that make sense? Okay. So then by intuition, I'm thinking I can compare this one with n over n squared. What's n over n squared? Which is 1 over n. And 1 over n is a famous divergent harmonic series. Does that make sense? Okay, so with all this intuition, so you think, okay, let me try to use limit comparison test, right? To compare this one with 1 over n series. So I'm going to take a ratio of this one with 1 over n. So we'll take a ratio of that, ln of n divided by n squared, then divided by 1 over n. I do the calculation, that's ln of n divided by n squared multiplied by n over 1. I simplify this, I get ln of n over n. All right. So now I know limit comparison test tells me 3 results. The first result is the limit of ratio equals to a finite number. If the limit of ratio equals a finite number, that means an equals to a number multiplied by bn. So these two numbers, so one is a multiple of the other. Think about 3 and 15. Yeah, think about a number like a multiple, right? So one is a multiple of the other. So those two are very closely related. So in mathematics, we just say one scales the other. If you think about transformations of functions, there's one transformation called dilation. So dilation is basically a scaling, right? If I multiply by 2 with someone, I increase the quantity by 2. If I multiply by half, they shrink to half. So we call scalar. So those two just differ by scalar. That means they're closely related. Think about 3 and 15 or 5 and 15. So if one converges, the other converges. One diverges, the other diverges, right? Or second situation of limit comparison test. If the limit equals 0, if the limit of the ratio equals 0, then if the denominator series diverges, then the numerator diverges. So we are going to use this one, right? Because we know 1 over n is a divergent series. So we want to fit into the second situation. We want to see the limit of the ratio equals 0. The limit of ratio equals, hold on a second. Hold on a second. Let me see. No, okay, the second situation is the limit equals 0, and if the denominator converges, the numerator converges. I was thinking I was making a mistake, which I was right about myself, yes. So when the limit of the ratio equals 0, if the denominator converges, then the numerator converges. And the third situation is, oh, right, we use the third situation, but we won't get the third situation because third situation is the limit does not exist. The limit does not exist if the denominator diverges, then the numerator diverges. Oh, hold on a second. So 2, when we take a limit, the limit does exist. The limit does it, right? The limit does exist. The limit is 0. So the limit of the ratio equals 0. Right, so we cannot conclude this. The second one, we won't be able to conclude. So the second one is inconclusive. Let's see, let's go step by step. Because we won't be able to use the second one, because the second one tells the denominator one converges, right? So if the ratio, if the limit of ratio equals 0, we want the denominator one to be convergent. But here we're using harmonic series. And of course, harmonic series diverges. So we won't be able to use the second one. And we won't be able to use the third one also, because we do have limit equals 0. The third one says that, you know, the denominator series diverges. If the limit does not exist, then we can conclude the numerator series diverges. But we don't get those. We don't get the second one. We don't get the third one. So we have to do more mathematical analysis. So we did get a ratio equals 0. However, the denominator series is a harmonic series. It diverges. So here, right? So the limit is 0, but the denominator series diverges. So the limit comparison test does not provide any information. So it's inconclusive. So it's inconclusive. So ideally, if we could get a limit does not exist, right? If the limit here does not exist, we can conclude because the denominator series diverges, so the numerator series diverges, but we don't get that. So we do get the limit equals 0. So it's inconclusive by the second part, so what do? So we compare 1 over n squared, we compare with the p series. So when we compare with the p series, if we compare with the p series, you know, the limit does not exist. But the p series, so 1 over n squared converges, right? It converges. But this goes to infinity, also inconclusive. Right? Because the limit comparison test says if the limit does not exist, the limit goes to infinity, and the denominator series diverges. Then we can conclude the numerator diverges. However, we have 1 over n squared. The denominator is a p series with p equals to 2, which converges. So we won't be able to use the 2. We won't be able to use the 3. So 2 doesn't work, inconclusive. And compare with the p series, inconclusive, right? So the test doesn't provide any information, inconclusive. So now we try a series between the two, and we already tried choosing the series of 1 over n cubed divided by 2, which means n cubed square root of n cubed. So this is a p series with p equals to 1.5. Well, 3/2 is bigger than 1, so this p series converges, right? So this p series converges. So ideally, if we could use the third one, the second one, if we could use the second one says, okay, if the denominator converges and the limit goes to 0, then we can conclude the numerator series converges. Okay, let's see that one. So 1 over square root of n cubed is a p series, is a converging p series, a convergent. So ideally, if we can compare those two, get the limit of ratio equals 0. Let's see if we can get that. So we take a ratio of these two, so ln of n divided by n squared, then divided by 1 over square root of n cubed. Right, we do the calculation, then what do we get? We get ln of n divided by square root of n. Right? Again, this is an indeterminate form. So when n goes to infinity, ln of n goes to infinity, square root of n goes to infinity, infinity divided by infinity is indeterminate form. So what do? L'Hopital's rule. So compare their velocity. We want to see who grows faster. When n approaches infinity, we want to see who runs faster than the other. So using L'Hopital's rule, we get this. Do the calculation. In the end, we get a 0. That's a bingo, right? That's what we want. That's what we want. So limit of now goes to 0, and the denominator series is a p series. 3/2 is bigger than 1. It converges. That concludes the numerator series also converges. All right, so this example, I like it too, because he tried 2 ways, right? You try to compare with the harmonic series with the divergent series. It doesn't work because we don't get to go to infinity. The limit of the ratio does not go to infinity. The limit of the ratio goes to 0, but the denominator series diverges. So it's inconclusive by limit comparison test. Then we try that again by 1/n squared with the p series with p equals to 2, which is a convergent series, right? Which is, if it's convergent, and we would want the limit goes to 0, but we don't. We get a limit goes to infinity. So that doesn't help either. That doesn't help either. So then we think use a p series in the middle of a harmonic series and p equals to 2. So which is p equals to 3/2. So 3/2 is bigger than 1, it's convergent. Now all we need is the limit of ratio goes to 0. If the limit of ratio goes to 0, we have this denominator series convergent. Then we can conclude the numerator series converges too. So that's what we did. Okay? So we compare, we take the ratio of those 2 series, then we take a limit. It does go to 0. So the denominator series converges. So the numerator, we conclude the numerator series convergent also. This is a good example. So the example, so example B, example B, C are good examples. There won't strenuous be questions like this on the final, right? I have no idea. Try the homework, Ali. I know I assigned a lot of numbers for homework. Hopefully you have time to try them. All right. Again, exams will be extracted from your homework sets. Okay. Okay, any other questions? Also, on the midterm, right? I think on the midterm, 2 or 3 questions from the examples of the textbook. I don't know if you have noticed. So in the final, you know, I may also pick some examples from the textbook. So make sure you go through the textbook examples, because some of the examples are classic, you know, are classic. Classic means so many people have worked on them, you know, they find a smart way of doing it, of dealing with it. So all we have to do is just to remember them. That's it. We don't have to reinvent the wheels. We just have to know to use them. So that's a good thing about, you know, redo the examples in the textbook. All right, anyone has any other questions? Okay, now you try 517. I really want to hear the rest of you. I see Alejandro is here, Li Zhen is here, Alexander is here, Bi Xin, Darren May, Fu Jun, Jack, James, Kelly, Luzette, Trey J, Zanep, Zachariah, Woodley. I really want to hear from all of you. But so far, I only see Ali, Damon, Rajev, Raw, Zachariah, Bishin, James, Jack, Zainab, Shahaya, Damon, go along. Okay, all right. Yeah, please show me, you know, you are in this class and you are thinking what I'm thinking. All right, let's all try this one. This one is a tricky one, right? But you see 5n, you see over 3n, that give you some hint. Yeah, try this one. I'm going to get some water.
Are we doing the checkpoint or the 5.4?
Oh, checkpoint. Do checkpoint. Sorry, let me make this. Do checkpoint. Do checkpoint. That's fast. Okay, so convergent. So limit equals to half, limit equals to 1. So which one you come? Okay, so you're comparing with 5n over 3n. Diverges. Okay, Golem says he's comparing with 5 over n with 3 over n plus 3. Huh. Why you want to compare with that? Okay, that carry says, yeah, 5 over 3 raised by n diverges. My mistake. Paul says, got limit equals to half. Limit of what equals to half? You compare, which one you compare with? Ali says, got limit equals to 1. Right. Okay, so limit equals 1, right? So basically, we just compare this one with 5 over 3n. Yes. So we compare with 5 over 3 raised by n. Then the limit equals 1, which means the two series scales each other. So one is a multiple of the other. So one converges, the other one converges. One diverges, the other one diverges. And we know 5 over 3 is bigger than 1. So this geometric series, because ratio is greater than 1, it diverges. So that's why this one must diverge also. Great. Great. So that's it, right? We compare with 5 over 3 raised by n, which is a geometric series. Geometric series, if the ratio is greater than 1, it diverges. If x raised by n and x is greater than 1, it diverges. Okay, you can put x like that. Okay, yes, like in this case, it's called a geometric series, right? So each step is just multiplied by a ratio, a common ratio. Yeah. Yeah, x is a ratio. Usually we use r. We say r raised by n. The ratio r. Yes, you're right, Ro. Okay, anyone has any questions? I think today we have a little time to do more exercise. Which rule would that be? The first one, limit comparison test. The first one, when the limit equals to a finite number. The first one. The first one says, but limit comparison test and the comparison test are used very often, especially limit comparison test. Because a lot of times we don't have a comparable series at hand. So the first part is saying if the limit of the ratio equals a finite number, one, or doesn't matter as long as it's a finite number. So that means one series scales the other, or one series is multiple of the other. So what happens to one? It happens to the other one. So the first one is very useful. When the limit of the ratio equals the number, not 0. We don't want to be 0. 0 would be the second situation. If the limit of the ratio is 0, ideally we want the denominator one to be converges. Then we can conclude the numerator converges. If the limit of the ratio goes to infinity, which means the limit does not exist, then ideally, if the denominator one diverges, we can conclude the numerator one diverges. So the example C is a very good example. Show us, one way doesn't work, the other way doesn't work. Then to be smart, find one in between of the harmonic series and the P series. Okay, so we have a little more time. Let me see. So next class, we're gonna let's just practice this one, because this one is important. The limit comparison test. It's important means it's very useful. Which one should we go? Oh, some of them takes time. Okay. 205, assign 205 as your homework. It takes a little time for you to do it. Yeah, 211 takes a little time. Those are interesting ones, but takes a little time. All right, so let's see which one we should choose, because we didn't do anyone with factorial. Let's do let's do 200 factorial ones. Yeah, let's do one with factorial. So let's do 200. You try and I try. Let me try to remember this. Right, so comparison test, especially limit comparison test, works with factorial very well. So let's see, 1 over n factorial. Can you compare with 1 over n squared? You want to compare with p series? That wouldn't work, right? That wouldn't work. So right, the textbook doesn't have any example of this, but I remember when I was a student, I did a lot of, let me think. This wouldn't help, because this will get a limit equals to, limit does not exist. Limit does not exist. I need a denominator series to be divergent. Right. So this textbook is choosing by the department. So in the beginning, if I had a choice, I would like to choose Stewart's book, because I learned from Stewart's book, but I was told to use this one. So forget about the factorial for now. I will figure out myself first, because I forgot myself. But I remember it was very easy to use a limit comparison test. But however, because we didn't talk about any factorial, I know 1 over n factorial must diverge, because it goes to 0 very quickly. But which one to compare? I just couldn't think about anything to compare. But if we compare with 1 over n, right? 1 over n is a harmonic series, it diverges. So we would need the comparison to go to not exist. Oh, maybe you're right. So if we take a limit of that, right? We do 1 over n factorial divided by 1 over n. No, the limit will go to 0. So this one doesn't work. The limit go to 0, we would need the denominator series to be convergent. Then we conclude the numerator convergent. So if we want to compare with a divergent series, we want the limit of the ratio goes to infinity, which means the limit does not exist. But no, but if we compare with 1 over n harmonic series, we get a limit equals 0. So let's all think about it. I remember this one was using limit comparison test, very easy. So let me change one so we don't waste time. Let's do 197. Okay, let's do 197, 196. So those two are good examples. So we should be able to do those two. Yeah, 197 is easier because we had an example 197. So let's all try 197. What do you mean by that, Ali? Both converge at 1. Oh, you mean both converge at 1. Right, okay, when you take a limit of ratio that equals to 1, which one you compare to? 1 over 2n? I see, that's okay. So it's better to use, okay, if you use 1 over 2n, that's fine, because you know 1 over n diverges, so 1 over 2n must diverge as well. Then when you compare, you take the limit equals 1, then you see because the denominator diverges, so the numerator must diverge. Yes. So the first part of limit comparison test is very useful. I agree with you. What about the rest of you? Or you could just compare with 1 over n, right? When you compare with 1 over n, the limit is half. Oh no, it's different, Ali. 1 over 2n is not the same as 1 over 2 raised by n. Yes, it diverges. So you compare with a harmonic series. You compare with 1 over n. So when you take a limit, no, that's not dumb, that's okay. So when you take a limit, you get a half, right? So we compare with 1 over n, the harmonic series, the famous harmonic series divergent. So you get limit equals a half, because half is a number. So if one converges, the other one converges too. If one diverges, the other one diverges. And the 1 over n harmonic series diverges, so this one must diverge. Okay, so keep doing the homework, all right? Anyone has any questions? Is this a monotone increasing theorem question? Sometimes in the middle. Actually, in reality, in life, we just don't care much about monotone increasing. You know why? Because in our exams, you know, most likely they're monotone increasing or monotone decreasing series. So that's for pure mathematics. So monotone increasing theorem, monotone decreasing theorem. Yeah, so don't worry too much about that. But stick with limit comparison test, yes. Because, you know, this section is talking about limit comparison test. So just try with that. Sometimes we just use monotone increasing theorem for granted. We don't even think much about it. 190A would be P series comparison. 190A, yes, you can compare with 1 over n squared, right? Yeah, the denominator is bigger. So the whole thing is smaller, right? If it's smaller than the convergence series, so it converges. Yes. All right, so keep trying your homework, okay? Trying homework, do homework will help you to understand the concepts better. Anyone has any questions? All right, if not, I will assign you homework and I see you on Thursday, okay? All right, good night. Good night.